Discrete mathematics is a very important branch of mathematics. Now we start with unit number 2 of discrete mathematics, that is lattices and Boolean algebra. Now lattice. A lattice is a poset in which every pair of elements has both a least upper bound and a greatest lower bound. On a lattice, we have following well-defined binary operations. This is read as A meet B denotes the greatest lower bound of A and B, and A join B denotes the least upper bound of A and B. We denote lattice L along with the operations of join and meet as L join meet. Now see what is lattice. First of all, lattice is a partially ordered set in which every pair of elements, means if you consider any two elements from that lattice, then for that two element set it has a least upper bound as well as greatest lower bound. Now we define two binary operations on that lattice L as one A meet B, which is greatest lower bound of A and B, and another A join B, which is least upper bound of A and B. Now together with these binary operations, we denote the lattice L as L join mid. Now first example, show that D6 divides is a lattice. So D6 is the set of all positive divisors of 6 which contains 1, 2, 3, 6. Now this is the hash diagram of D6. So if you draw the diagram, then it is easy to write the least upper bound and greatest lower bound for every pair of elements from D6. Now D6 is a partially ordered set, means poset with respect to partial order relation divides. Now to show that it is a lattice, we have to show that for every pair of elements least upper bound and greatest lower bound exist. Now the different pairs are like 1 2, 1 3, 1 6, then 2 3, 2 6 and 3 6. Now this is join and this is mid. So 1 mid 2 means greatest lower bound of 1 and 2. Now the lower bounds of 1 and 2 is 1 only. So greatest lower bound is 1. Same way, greatest lower bound of 1 and 3 is 1. Greatest lower bound of 1 and 6 is also 1. Now for 2 and 3, only one lower bound is there, that is 1. So greatest lower bound of 2 and 3 is 1. Same way, find the least upper bounds. Now for 1 and 2, the upper bounds are 2 and 6. So for 2, 6, 2 is the least upper bound. So 1 join 2 is 2. Same way for 1 and 3, upper bounds are 3 and 6. 3 is the least upper bound. So 1 join 3 is 3. So in the same way, we can find for all pairs least upper bound and greatest lower bound, that is join and mid respectively. And hence we can say that D6 is a lattice. Now these are some properties of lattices. Theorem 1. Let L be a lattice and A, B, C are elements of L. Then A precedes A join B and B precedes A join B. That is, A join B is an upper bound of A and B. If A precedes C, B precedes C, then A join B precedes C. That is, A join B is the least among all upper bounds of A and B. A meet B precedes A and A meet B precedes B. That is, A meet B is the lower bound of A and B. If C precedes A and C precedes B, then C precedes A meet B. That is, A meet B is the greatest among all the lower bounds of A and B. Next theorem, let L be a lattice. Then for every AB in L, A join B is B if and only if A precedes B. A meet B is equal to A if and only if A precedes B. Means for two elements A and B, if A precedes B, then A is the greatest lower bound. If A precedes B, then B is the least upper bound. Now if A meet B is A, if and only if A join B equal to B. Now there are some more laws. In any lattice L, following properties hold for ABC belonging to L. Now first is idempotent laws, that is A join A is A and A meet A is A. Commutative laws. A join B is equal to B join A and A meet B is equal to B meet A. Associative laws. A join B join C is equal to A join B join C, and A meet B meet C is equal to A meet B meet C. Absorption laws. A join A meet B is A, and A meet A join B is equal to A. So one more theorem for ABC belonging to L. If A precedes B, then A join C precedes B join C, and A meets C precedes B meets C. Then second, A precedes C and B precedes C if and only if A join B precedes C. C precedes A and C precedes B if and only if C precedes A meet B. If A precedes B and C precedes D, then A join C precedes B join D. A meets C precedes B meet D. Now we will see some special types of lattices. Now first is bounded lattice. A lattice L is said to be bounded if it has both greatest and least elements. Now already we have seen that greatest element is denoted by 1 and least element is denoted by 0. If L is a bounded lattice, then 0 precedes x and x precedes 1 for all x in L. See why? Because as L is a bounded lattice, it has a least element 0. So by definition of least element, 0 precedes x for all x in L. Now as it is a bounded lattice, it has a greatest element say 1. So by definition of greatest element, x precedes 1 for all x in L. So by combining, 0 precedes x precedes 1 for all x in L if L is a bounded lattice. Now A equal to ABC, then P of a subset is a bounded lattice since it has the least element phi and the greatest element A. So already we have shown this part as a lattice. So from the Hess diagram, it is easily observed that phi is the least element and A is the greatest element. So P of A with subset is a bounded lattice. Consider the lattice L of natural numbers with usual less than or equal to relation. So L is 1, 2, 3, 4 and so on. Now usual less than or equal to means for AB belonging to natural number set, A is related to B if and only if A less than or equal to B. Now 1 belongs to L and 1 precedes X for all X in L because 1 is less than or equal to all natural numbers. So 1 is the least element, but there is no greatest element in L since there does not exist any G in L such that X precedes G for all X in L. So this lattice is an unbounded lattice. Now the lattice R is not bounded since it has neither greatest element nor least element again with respect to usual less than or equal to relation.